Everyone, we are going to get into our XRD lab, specifically an investigation. So you're all private eyes for the purpose of this lab. We will be analyzing a lot of XRD data. We unfortunately don't have an XRD at this point, but we have real data taken from myself. In my studies. So we're going to utilize that data and we are going to kind of investigate what material we have. We're going to look at the differences between metals and polymers, semi-crystalline polymers and amorphous polymers. We're going to derive selection rules using our structure factor equation in order to delineate between different structures. So we're going to be looking at BCC structures. We're going to be looking at FCC structures. We're going to be looking at diamond structures. We're going to be looking at zinc blends and superlattice structures as well. So I think it's going to be a pretty engaging lab, even though we don't actually get to put the powder in the XRD. But again, we have videos to support that so that you can kind of understand how the data was collected. So let's get to it. So again, for X-ray diffraction, when we see these kind of signals that appear in our XRD, we are going to only see signals when we have effectively perfect constructive interference. So when we have an incoming and a scattered waves, when they interact and they're in phase, so again, waves in phase difference, 0, then we see essentially that change in amplitude here. If there's destructive interference, if there's, again, if there is a difference in that, the phase, obviously then we're not going to see a signal. And again, that is going to allow us to determine what I like to call characteristic distances in materials. So distances that effectively occur throughout the material. And that's, you can imagine, right? Like we're not pointing our X-ray at a very particular single atom or plane or very specific plane of atoms. It's hitting everything. We're going to see these consistent distances that reoccur in a material. So we're going to be using copper alpha radiation in this experiment, 1.542 angstroms. And again, we need to use that because we need to investigate our lambda has to be on the same order as the distances between the structures that we are trying to investigate. So that is the critical criteria that we have to have. So that's effectively the goal here. So we're going to use copper alpha radiation because we're looking at angstrom and nanometer size structures. And we need regularly spaced array of obstacles, first condition for diffraction. We need the distance and the wavelength to be commensurate on the same order. And then we need constructive interference. So let's go ahead, get to this next one. Now, we've seen Bragg's law in this course, and you see it typically represented as this DHKL. And again, the HKLs refer to essentially our Miller indices. So for our planes that we've kind of discussed a bit in the class. However, this is the most general form of diffraction in Bragg's law. And you can see here that we are looking, we're looking at here, we can see that this is a general expression. So this D here is not DHKL, the interplanar spacing. It's just some general or characteristic distance between our materials. And this is important because when we get to amorphous structures or semicrystalline structures, those do not have this kind of crystalline behavior or fully crystalline behavior that we observe in metals. So you're going to see a difference in your basically in the diffraction pattern that we observe. So you're actually going to see basically peaks getting wider and basically the width of those peaks increasing. And again, the width is because we're getting diffraction from other distances. So it's not this kind of preserved distance that occurs, throughout your material. So for example, let's see if I can write on here. Yes, great. In crystalline materials, we know like there is this distance, and that distance repeats everywhere. But if I have, an amorphous material, well, there might be some nearest neighbor distance, but then things kind of get, if you're looking for characteristics, it gets kind of fuzzy. So instead of having just a sharp peak occur at that particular distance, there may be several distances here that are kind of the same, characteristic size. So you may get a peak that has a certain width to it. And again, the wider the peak, that means the less long-range translational and orientational order. So if that is a delta function, we have significant long-range translational orientational order. If we have larger or wider peaks, excuse me, then that will indicate to us that we have short-range order, but not necessarily significant long-range translational order. And excuse for the title, I'll have to fix that later. It's not constructive versus destructive for everything. Again, we are going to be looking at cubic structures in this experiment. So we're going to be looking at body-centered cubic, face-centered cubic, and some structures that we can basically translate into a basis that fits essentially these cubic structures. Now, there's obviously, we have these 13 basically cubic structures. Simple cubic structures are the most, cubic structures have the highest degree of symmetry. So we have our 3 lattice parameters are all the same, are equal, and then our angles, which are alpha equals beta equals gamma equals 90 degrees. So all of our lattice parameters have the same magnitude. All of our interaxial angles have the same angle, and this is obviously different from triclinic. Oops, is it not letting me draw anymore? Uh-oh. Well, anyways, let me see if it's letting me draw. But if not, it's okay. Nope, I've lost it. I've lost the power. But anyways, triclinic has the lowest, lowest degree of symmetry. So, if we have, again, materials have short range order, but not necessarily long range order significantly, and you'll see essentially this. Radial distribution functions, again, we can actually perform a Fourier transform of our PDF and RDF that we've discussed in class, and you can actually get your XRD plot. It's very complicated, and we won't be doing that in this course. But again, it's the same kind of idea of inverse space and Fourier analysis. So it's really it's critically related essentially to these concepts, but you can do that in another class. So when we look at these materials, we can, again, it's very clear, these just sharp, almost like delta-like functions. This is a crystalline material. Here, again, depending on the width and depending on the number of peaks, it could be an amorphous solid, or you can just have effectively a gas as well. And then you can see the difference here. This darker curve is amorphous germanium. And you can see it only has a few peaks, and then it just kind of, decays off. But here, for crystalline or semicrystalline germanium, you see more peaks. So more peaks, sharper peaks, those are going to be semicrystalline versus amorphous, and it'll be very germane, no pun intended, to the conversation that we're going to have today. PMMA and PMO. PMMA, and PEO. Actually, speaking of germane to the discussion, I'm going to see, I want to see if I can write. No, I can't. Is it not allowing me to draw anymore? Excuse the delay, but I would like to. My pen is not working. Sometimes I have to plug it in just to kind of wake it up. And apologies for the delay, but again, you all know that these are live videos. There we go. Now we're active. Now we're drawn. All right. Just needed to wake it up. All right. So PMMA is a amorphous polymer. So this is an amorphous polymer. So you are not going to see really any significant crystalline regions. PO and PEG, that is a semicrystalline polymer. So we should expect that should have sharper peaks. This should have wider peaks and fewer peaks. Sharper peaks and more peaks for this one. Again, PO and PEG is actually a very interesting polymer. We call it a stealth polymer. It has hydrophilic and hydrophobic regions. PMMA is used a lot. A lot of acrylics are made of PMMA. Bone cement utilizes PMMA. So it's a very cool polymer. But yeah, this is also called a stealth polymer. I always like that because of the. I like that because basically it's used to coat and to be biocompatible, to like coat drug delivery to make sure. But anyways, discussion for another day. So we have several candidates and materials that we are going to investigate in this lab. So copper, aluminum, platinum. those all have an FCC structure. So in the XRD data that we are given, it could be, again, these are some potential candidate materials. So these are all the suspects. Again, I watch a lot of like crime dramas and Bones and Castle. So, but anyways, procedural cop show. But anyways, copper, aluminum, platinum, those all have FCC structures. So we need to determine, and there's, when we try to figure out what material correlates to what XRD plot, we are going to be looking for the calculation of lattice parameters to give us a hint, and we can kind of correlate that to atomic radii potentially. But one of the key things is seeing in the XRD plot and seeing the HKL indices that the peaks represent and where they occur, we are going to derive selection rules. So there are selection rules specific for FCC structures, and we are going to derive those rules and see if those HKL indices appear on our plots. So that's going to be the one of our key characteristics. Same thing, chromium, tungsten, molybdenum, those all have BCC structures. So we are going to use that as well to figure out those things. NaCl, salt. NaCl has this kind of interpenetrated lattice of which one do you think is bigger? Always the anion. So these are Cls, these are Na. It's this interpenetrated lattice. It's really basically a simple cubic lattice. So you could represent it as such. So just simple cubic, for each of these kind of structures in here. But it's interpenetrated lattice of, basically these Na and Cl ions. And we'll get more into that structure and how we are going to calculate selection rules for this. So the interesting thing is here is you should expect to see kind of super lattice peaks show up. So peaks that are different in magnitude depending on whether the diffraction basically adds these two diffraction components or if they subtract. And that'll become clear once we start to derive things. CSL has a similar structure, but whereas, again, it's an interpenetrated lattice, but whereas these can be represented as FCC, basically interpenetrated FCC lattices, and you can kind of see that in the structure here, like this is a big kind of FCC. Here, it's going to be two interpenetrated BCC structures, and we'll get to that. But CSL is also a candidate. Also, tin and silicon have a diamond structure, which is also a different type of interpenetrated FCC lattice. And again, we'll get to that in a bit. Excellent. So let's go ahead and actually let's take a before we get into this, let's derive it and let's look at discard all the notations there. Let's take a peek at our lab handout, which I hope is here. Downloads. Actually, it's on what am I talking about? So this is our official lab handout for our lab. That was super redundant. Again, learning objectives, we can kind of see what we're going to be looking at for these materials. Obviously, we are going to utilize Bragg's law. We're also going to heavily utilize this expression. So given the HKL indices, or what we think that they are by matching our XRD data to what we are working with, we are going to calculate lattice parameters and then compare to the real material. So that's going to be a critical tool that's going to allow us to compare our data. Excuse me. That is embarrassing. Again, we have different expressions for different structures, and we could have investigated many of these, but we are going to keep it a little bit more straightforward and focused on cubic materials. So we're going to utilize this expression significantly. But one of the key things that we need to do is we have to, again, Bragg's law will tell us the conditions for diffraction, but we don't have any information about peak intensities. So determine peak intensities and basically what types of interplanar spacings or HKL indices will allow us to even see like the conditions for diffraction. We have to calculate the structure factor because our intensity scales as the structure factor, the magnitude of the structure factor. So anyways, we'll get to that in a bit. Now, this is, without question, a nasty looking equation, but it's actually, again, in my opinion, or not in my opinion, but again, I think that we can handle this and we can work through this together. So N, capital N, is the total number of atoms in our structure. So if it's FCC or BCC, the total number of atoms, we'll get to that in a bit. Each atom, N, will have some XYZ coordinate. So that is a key component here. And HKL, we are going to figure, depending on what is allowed and what is not allowed, or what exists and does not exist in terms of our the HKL indices that appear, then we're going to determine essentially our selection rules. So that's a lot of words. Let's actually do an example. So if we have a BCC structure, we've talked about that in class. So if we have a BCC structure, so this is BCC. So we have a BCC structure. We can, and we will, we'll have how many atoms? 2 atoms. Because BCC has 2 atoms, we know FCC has 4 atoms, and simple cubic has 1 atom. So my total number of atoms for BCC is 2. And I'm going to select, actually, not this guy. I'm going to select my origin, and I'm going to select the center atom. I'm going to choose these as my basis. So these are my atomic base. I could choose anyone, but you're going to see that this is going to be very convenient. So let's start to tackle this expression. So I'm going to have F of HKL equals, so I'm going to do F, so it's going to be F times exponential of minus 2, well, actually, so if I plug in, actually, let's write it out the full way first. Exponential minus 2 pi I times h times 0. Again, I'm going to do this once. Times 0, k plus L times 0 plus f exponential minus 2 pi I times basically h over 2 plus k over 2 plus L over 2. Make sense? So what happens to that first component? Well, HKL becomes, what's an exponent? What's anything times 0? 0. What's exponential of a 0? Doesn't matter. We don't have to think. We have Mathematica. We'll be okay. It's all right. So there should be no worries. But let's go ahead. Let's open it up. Let's get this moving. So let's do exponential of 0 in bated breath. 1. So we just have f. So now we have f plus f exponential of minus pi I times h plus k plus L. So let's start to think about some values we can plug in. So let's start off with, what if I have like a plane that's like 1, 0, 1. So if I plug those values in for h, k, and L, that's going to give me, and let me kind of pull this to the side here. Let's go ahead here. And so that's going to leave me with exponential of minus pi times I, and then what's h plus k plus L of 1, 0, 1, so that's going to be 2. So that gives me 1. So that works, right? Because they add, they're not going to cancel each other out. So this is going to be allowed. Yay! It can exist. What about 1, 0, 0? Well, if I plug in 1 here, because this will lead to f plus minus 1, which is minus f. So this is not allowed. Okay. Let's see if we can find a pattern here. What about 1, 1, 1? So let's put in 3. That's going to be 3. That's not going to work either. What about 2, 0, 0? that works. What about 2, 2, 2? So that's 6. That works. What about 5? That doesn't work. What about 7? So you start to see the pattern. So hopefully. So we can deduce that if H plus K plus L, if this is odd, we will not. So we don't see a peak. No peak. Structure factor is 0. If H plus K plus L is even, on the other hand, this is allowed. So we will see a peak. So if we look at an XRD plot, for example, we will only see peaks if it is a BCC structure. That's the key caveat here. If it's BCC, the only allowed peaks are if H plus K plus L is even. So this is fantastic because when we compare our experimental XRD plot to something from the basically it's a printout from the International Crystallographic Structure Database, which is a very, very, very expensive software that basically allows you to measure, or actually to compare your data to, again, like the International Crystallographic Structure Database, where they compile all of their crystallographic structure data. So it's a very, very, very useful tool. So this is fantastic. So we're going to be able to do this. How would this change if we have an FCC structure? Well, in FCC, we know our number of atoms is going to be 4. And we can draw our picture like this. I'm trying to draw faces. So I can choose my basis. 0, 0, 0 is obviously a fun one. Then I could do 0, 1/2, 0. I can do 0, 1/2. Actually, that is, actually, excuse me, 0, 1/2, 1/2. Let's do 1/2, 0, 0, and then let's do 1/2, 0, 1/2. So I can choose these 4 as my basis. And I could do the same thing for FCC, and we can figure that out. So that is a key factor in determining these, basically these structure factors. So those are explained a little bit. So you want to derive these for the structures that we may encounter first. So BCC, aren't I so nice? I mean, it's in the lab handout. I'm doing it on the video. I'm just joking. Not really, but it's true. But anyways, but we can go a little bit further here. And let's go ahead and do, how would NaCl look like, for example? So let's go ahead and calculate the structure factors for NaCl. Yeah, NaCl, and we can kind of see this here. We saw previously in our slides that it's a cubic unit cell, but it can be visualized as this basically FCC interpenetrated array. And we can actually, let's go ahead and look at that here. Let's go back. Yes, let's, don't save. Again, everyone knows where it's live. So if we look at, for example, NaCl right here, and again, we know the big structures and little structures there, we can actually go ahead and you could do a very complicated method, which is taking basically the 2 FCC lattices and then summing them together, because effectively that's what we're doing here. But you can also notice here that we can do a little trick. So you can actually write this as a 2-atom basis, like BCC, where we have, because basically these are almost like cubic unit cells, right? So if you look at these unit cells, you can just approximate it as a cubic unit cell. And we can just shift the basis. So we can actually say the following. We can treat it as, we're going to have our Na, for example, and then that basis is going to be at 0, 0, 0, and our Cl will be at 1/2, 1/2, 1/2. So the key difference here, really, it's going to be very similar to our BCC calculation, but we're going to have a little f of Na and a little f of Cl, and there's going to be a little bit of nuance to this. So I can calculate, I know that my structure factor is going to be equal to little f Na, and we know we can plug in those coordinates and it'll be 0, plus little f Cl, and then we can also see that we will have basically exponential of minus pi I times h plus k plus L. So there's a key distinction and difference here, though. And let's break it down. What happens when we have h plus k plus L equals 1? So let's go to our Mathematica. Remind ourselves. So we have exponential of minus pi times I. And again, you gotta wake up Mathematica. I should not hum that. Public domain. I don't want to get the the audio flagged. But hopefully we remember from the next time. We have to wake this up anyways, because next we're going to get into our data analysis section. So, but we're going to see something actually quite interesting here. So one of the things you can notice already is that for our selection rules, really we're going to see, so that'd be -1. So if h plus k plus L is odd, we are going to see FNA minus FCL. If h plus k plus L is even, then we will find that FNA plus FCL. So you're going to have actually lots of different allowed quote unquote basically HKL indices, but the difference is going to be in the magnitude. So if you see kind of this common pattern where h plus k plus odd is smaller and even, basically these are superlattice structures. So you're going to see a difference in the magnitude of the peaks, because remember that my intensity is proportional to f squared here. So those would be your selection rules. You can do something very, very, very similar for CSCL, so those types of structures as well. And you can kind of work on your own. Hopefully this has been a big enough of a hint for your silicon as well. So that's all the pre-lab. So in the next video, we're going to get into the actual data analysis and how we're going to kind of combine these two approaches to basically solve that murder, figure out what that material is. Thanks. See you in the next video. Bye.